All right, well, as we get going here, our next talk this afternoon is about reversing Bluetooth low energy continuity protocols for tracking OS fingerprinting and behavioral profiling. I'm not going to say that 3 times fast, but Sam Teplov is here to speak to us about that. So let's give him a round of applause, please.
Good afternoon, everyone. My name is Sam Teplov. I'm currently a graduate student at the Institute for Software Research at Carnegie Mellon, and I'm part of the Furious Mac research group. And today I'm going to be talking about some of the work we've done in reverse engineering Apple's Bluetooth Low Energy Continuity Protocol and some of the security and privacy concerns that come along with it. So a little bit about the group. Furious Mac was first established in 2015 at the United States Naval Academy. We were mostly interested in hardware identifiers, and we still are. So a lot of our past work has focused on Wi-Fi MAC address randomization and trying to defeat randomization. And initially, this Bluetooth low energy research just started as a side project to see if we could use the data included in Bluetooth advertisements to actually defeat MAC address randomization in Bluetooth. And then it got kind of out of control, as you'll see. So this is what we're going to cover in the talk. We're going to first go over the methodology that we use to reverse the protocol. And then we'll go through a number of the different messages and fields that we actually reverse engineered. Some of the messages we'll talk about, they allow you to see the current activity of various Apple devices. You can actually learn the SSID of the network a user is connecting to whenever they attempt to connect to a closed network. We'll also talk about how we're able to do OS fingerprinting for iOS 10 through 13 and as well as Mac OS. And then we'll talk about, lastly, some of the privacy concerns associated with like being able to track users by defeating MAC address randomization. And then I'll attempt to demo our Wireshark dissector that we built, and we're going to put it out so all of you can actually download it and use it. So quick privacy warning, as part of the demo we're going to be sniffing Bluetooth low energy. So therefore, if you don't want us to sniff your traffic, we recommend turning your Bluetooth off for the remainder of this talk. So a little bit about Apple Continuity. You may know some of the features that it supports, but pretty much it was developed to allow for the seamless communication between various Apple devices. So some of the features that include handoff. So handoff allows you to start a Safari browsing session on your iPhone and then pick it up on your MacBook. There's also other features such as auto unlock, where you can use your Apple Watch to unlock your MacBook. And then there's also universal clipboard, some of you might have used it, or instant hotspot. So there's a bunch of different things that this protocol supports. So this protocol is completely proprietary. There's no open source documentation from Apple or anyone talking about it. So we actually have to reverse engineer it to understand the different fields and messages. So there's really one of 2 ways we could have gone, and we decided to go with the black box reverse engineering approach, where we would carry out different inputs on the devices, like tapping the screen, opening certain apps, and then we would observe how the messages changed. And so we first published our work back in the spring of 2019. Since then, there's another group that recently took a different route. They decided to build off of our findings, and they just published a couple weeks ago. And they actually reverse engineered some of the binaries that were used to that are used to create these messages. And so they were actually able to learn what the message names and field names are as written by the developers by pulling out the strings. Whereas when we did it, we kind of just named the messages depending on the functionality that we observed. So we kind of just made up names. So as we go through some of the different messages and field names, you'll see 2 names. You'll see the name that we gave it and then the actual name, just to make sure no one's confused. So this is the basic methodology we used. We had a very vast repository of various Apple devices. We had all different kinds of iPhones, ranging from iOS 8 to iOS 13, MacBooks, AirPods, HomePods. And we would bring them into RF stereo environment, and then we would carry out different actions on the devices, and we would use an Ubertooth to snip them, and then we would pipe that directly into Wireshark. And as we observe patterns in the traffic, we would dynamically change the dissector and recompile it. And so that's how we were able to figure out the fields and different message types. So this is what a general BLE advertisement frame looks like. So I just want to point out a couple things. Every single advertisement frame, it has a company ID that is related to the manufacturer. So for Apple, they're hex 4C. So that allows us to just filter specifically on Apple frames. Everything after the company ID, if you were to try to use Wireshark right now to sniff Bluetooth, none of that would be parsed out. And so everything starting after the company ID is the actual dissector that we wrote. And it follows a simple type length value format where you have the type of the message, the length, and then the actual data. and they can string together multiple of these messages in one advertisement packet. So these are the messages. I just wanted to highlight a couple of them. We'll go through some of them in more detail, but anything, when you use AirDrop, it sends out a message. AirPrint, even when you use Hey Siri on your phone, it actually sends out a Bluetooth message whenever you join a Wi-Fi network. So you can see the extent of these messages. So now we're going to go through a couple of them in more detail. So first is the AirDrop message. This message gets transmitted whenever a user attempts to AirDrop media to another user. And as you can see, whenever you use AirDrop, you're actually leaking the first 2 bytes of the SHA-256 hash of various iCloud account data, like your email, your phone number, and your iCloud account. There's actually research done by the guys over at Hexway where they created a hash table, and they're able to look up phone numbers for a specific area code. So whenever you use AirDrop, you're actually leaking all this information. The next message is the AirPod message. So this is sent whenever you interact with your AirPods, and it actually leaks a crazy amount of information. So you can actually see if someone's AirPods are in their ears, if they're out of their ears, if one's in the case, one's not in the case. And I'm going to attempt to demonstrate that in the demo. You can also learn the battery status on the right, left, and the actual case. You can see if they're currently charging or not. There's also a counter that counts how many times the lid's been open and closed. So this is not a good idea because whenever your MAC address rotates, the counter will either stay the same or probably go up by 1. So you can actually link together random MAC addresses. You can also learn the device color. Yeah, so it's a lot of stuff. The next message is the handoff message. This message is sent out whenever a user interacts with any handoff-enabled app. Some examples of handoff-enabled apps are like Notes, Safari, Apple Maps, so a lot of the Apple default apps. The first thing you'll notice is there's a clipboard status at the top. So you can actually, so this is for the universal clipboard feature. You can actually see if a user has recently copied something into their clipboard or not. The next 2 bytes are the initialization vector, which we call a sequence number. And so we'll come back to this later, but this really enables you to track users over time despite MAC address randomization. We'll go into it more a little later, but it only increments by 1 when they carry out actions, and over a 2-byte space, it's actually feasible to track users. The next message I'll talk about is the Wi-Fi settings message. This gets sent out whenever you navigate to the Wi-Fi settings page of your device where you can pick what Wi-Fi network you want to connect to. And it contains this 4-byte iCloud ID. And what's neat about this is that every single device on the same iCloud account has the same iCloud ID. So you can actually correlate all the different devices in a room that are linked back to the same iCloud account. And this message is used to, it triggers a different message, which we call a hotspot message. And so what this message contains is, in the various fields, it contains the battery life of your device, the cell type you're using, whether it's 3G, 4G, LTE, and also the cell signal. So this is kind of the flow that I can give you. So let's say you're on a MacBook and you want to connect to Wi-Fi. You go to a Wi-Fi settings page. It sends out that Wi-Fi settings page message with that 4-byte iCloud ID. And if there's a device within range that recognizes that ID, it'll send back the instant hotspot message, and it'll fill in the battery life and the signal type and signal strength. Yeah. Now, this is the Wi-Fi joining message. This is sent out whenever you join a Wi-Fi network. And like the AirDrop message, it also contains hashes of various phone numbers and your Apple ID. But it's worse because it's 3 bytes now. And then also, the last field contains the hash of the SSID you're joining. So in theory, what you could do is you could just create a hash table of all the different SSIDs in your area and just look up whatever network they're attempting to join to. And I'm going to attempt to demonstrate that later, too. The last message is the nearby message. This message is constantly being sent out by your devices. It's pretty much meant to inform other devices around your device of the current state. So we're going to break down some of the different different fields. So this first is the status flag. So there's a couple bits that just can be turned on and off, and they mean different things. For example, the least order bit, you can actually tell if the device is the primary device on an iCloud account. You can also see a user's AirDrop receiving options if it's on or off. And we're still trying to figure out a couple of them. The next one is the action code, and so this is the actual status of the device. So you can see if a user's phone is locked, if they're actively using it, if they're in a car or not, or if they're in a phone call or FaceTime session. So this is constantly being emitted from your devices, so you can learn the activity level very easily. And then the next field we actually found to be iOS dependent. So depending on the iOS you're running, it had different values in the field. So for example, iOS 10 had 0, iOS 11 had hex 10, and then starting in iOS 12, they started having 3 different values, and we actually noticed that they correlated to whether your Wi-Fi was on or off, or if you were actively joining a Wi-Fi network. So this allowed us to fingerprint OS 10 through 12. So you may be asking how we fingerprint 13. Luckily for us, Apple added this new field starting in iOS 13 called the transmission power level, which we did not observe in any other iOS version. So this is a picture, by the way, of our custom Wireshark dissector. You can see some of the fields broken out there at the bottom. So this allowed us to pretty much fingerprint iOS 10 all the way up through 13. Now for macOS, luckily they decided to flip 3 of the bits and the flags between MacBooks and all the other devices. So you're actually able to differentiate a macOS and BLE traffic compared to any other device. So what this allows us to do is now fingerprint iOS 10 through 13, and then also macOS. So now I'm going to talk about user tracking via the static fields. So per the BLE spec, they recommend that your random MAC address changes every 15 minutes, and with Apple they do. But they kind of forgot to change something else, which is the actual data in the advertisement field. So as you can see here in 2 examples, the MAC address does change, but the data stays exactly the same. So you can actually correlate random MAC addresses back to the same device because the data doesn't change at the same time as the MAC address. And then we did some pretty extensive research into, if you remember, I mentioned that sequence number, the initialization vector, in the handoff message, and we did some pretty extensive testing to see the feasibility of being able to use that sequence number to track people over time. And so what we did is we got a couple devices and we gave them to group members, and we tracked how that sequence number changed over time, and we found it to increase pretty slowly, only 470 over a day. And remember, it's a 2-byte space. And then what we did after that is we did a feasibility study where we went out in public and we tried to see if we were looking for a specific sequence number, if it would collide with any other ones, and we found that it's actually pretty hard to find collisions. I mean, up to a point. If you have too many users, you can't. But if you want to read more about this, you can read about our methodologies in our PETS paper. So now I'm going to attempt to do a live demo to demonstrate how our Wireshark dissector works. So it's probably not going to work. But okay, so it's actually working. So now I'm just going to filter out all incorrect CRC and malformed frames. Oh, that's not good. Can you see it now? Well, can I unmirror this somehow? All right, we'll attempt to do it like this. So you can see here, I have an iPhone running iOS 13. You can see right now it's locked, and then as soon as I unlock it, it says it's transitioning from inactive to active state. And now if I go ahead and unlock it, it'll say that I'm in an active user state. So that's pretty cool. So now I'm going to attempt to join a closed Wi-Fi network here. And now you should see the first 3 bytes of the SSID I'm attempting to join. So if you want, you can quickly hash all the different SSIDs out there and figure out what network I'm attempting to join. So this one's my favorite. This is the AirPods. So I have a pair of AirPods here, so I'm just going to play around with them. So you can see both AirPods are in the case. I'm going to take one out. You can see right out of case. I can take both of them out of the case. I can put them both back in. Yeah, so it's pretty cool. Yeah, so that was the quick demo. can't get PowerPoint back up. Okay, so we disclosed all this information back to, we disclosed this to Apple back in March of 2019, and they said they were working on it, but clearly not, because since then they've actually added more features and message types, so I don't really know what's going on there. We recommended that they encrypt messages, because a lot of the messages are being sent between devices linked to the same iCloud, so they should already have some shared key, so you should be able to encrypt them. We also recommended that they rotate MAC addresses stochastically and more frequently, and that when they do rotate MAC addresses, they actually change the data in the advertisement frame at the same time as the MAC address change. And then we also recommended that they change the way they generate the IV so it can't be used to track users. So this is our Wireshark dissector. We just put it up earlier today, so all of you can download it. We currently support the stable release of Wireshark and the old stable release. So feel free to download it. We're still working on reverse engineering a couple messages, so we could really use your help so we can finish this dissector. And so finally, I'm just going to leave you with a couple thoughts. Individually, each message might leak a small amount of data, but all together, they can be used to conduct OS fingerprinting, behavioral profiling, and user tracking. Thank you for your time, and I'll take any questions. Yeah, we used the Uber. Yeah, so he asked what kind of hardware we used in our lab to actually sniff the BLE packets. So we initially used the Ubertooth, but once you go to more public settings where there's a lot of devices and there's a lot of BLE traffic, the Ubertooth doesn't do really well. So we're actually using, for this demonstration, I'm using an NRF sniffer, which seems to work a lot better in larger public settings. But the Ubertooth is great when you don't have too many devices and too much traffic. Yeah. All right, if there's no more questions, thank you for your time.